Good morning. So in this video, I'm going to tackle diffusion in solids. You can find the materials from chapter 5 of Callister. So let me share the PowerPoint. Okay, so I'm going to discuss chapter 5 of Callister. This is about diffusion in solids. So why do we need to have some information regarding diffusion in solids? So for example, if you heard of carbon steel. So carbon steel is basically iron with carbon, So if you still remember the crystalline structure of metals, so for example, iron is an FCC. So there are interstitial spaces. I hope you still remember the concept of interstitial space. Basically, these are empty spaces, between the atoms. So what happens? What happens in the manufacture of carbon steel is that you're going to diffuse or insert carbon atoms inside the interstitial space between the iron atoms. So if you will imagine, this will make the material more tougher because there are lesser space available. So the interstitial space, the space between the iron atom is occupied by carbon. So that makes this material more tougher. And also in semiconductors, you have silicon, and then there are vacancies. So these vacancies, for example, you diffuse some boron so that you're going to produce semiconductors. So these are the application of this particular topic, diffusion solids. Okay, so we have here gears, no? So I've encountered gears like you when I'm still in college, in mechanics, by statics and dynamics, in the dynamic part. So of course, when we are a kid, probably you're familiar with this in your bicycles. Tapos meron siyang parang belt, and also in the, as you can see in this picture, we have the transmissions of a vehicle. So, of course, transmission, you have first gear, second gear, third gear, fourth gear, fifth gear, So as the gear number increases, the gear ratio, also increases. Okay? The gear ratio also increases. That means for every single turn of the primary gear, you will have several or more turns of the secondary gears. So that's how the gear works. So as you can see in the picture, somehow this moves from forward or backward, the primary gear setup moves forward or backward to obtain the first gear, second gear, and third gear. And di ba sinasabi nung ating teacher sa mechanics, ang gears daw hindi nasisira, no? Ang nasisira is usually the belts. Usually yung belts daw yung nasisira, yun yung pinapalitan. So bakit ba hindi nasisira yung gears? Kasi this is generally made up of iron, carbon steel, ano? Yung ginagamit na, especially in this area. So they heat treat this, and then in the process, carbon diffuse into this area. So what happened is that this area is more tougher than the inner part. Ito naman kasi yung nagiging in contact with the other gear. So kaya kailangan matibay talaga dito. Ano? So if you will imagine, sana na-imagine nyo, yung iron crystal, meron siyang mga interstitial space or meron mga space. Tapos doon pumapasok yung carbon. So it becomes, nababawasan yung available space. No? So it becomes more, the mechanical strength is increased by carbon diffusion. Okay. So, some place here. Ganito nag-work yung ano, yung speed, yung gears, na. So, pag gumagalaw lang yan, pag kumambyo ka, gumagalaw lang. Ito yung gumagalaw. So, halimbawa, pag itong dalawang gears na ito yung magkatapat, parang ito yung primera, ano? Yung isang ikot nito will result to, halimbawa, mga kalahating ikot itong pangalawa. No? So, mas mabagal yung ikot nito. Pero pag kumambyo ka, pag napunta ka dito, halimbawa, napunta ka dyan, no? So, yung isang ikot nito, several turn na nito. So, parang ito yung primera, tapos ito yung segunda. Ganyan lang naman yung transmission, di ba? Tapos, pag dito naman, pag nag-move ka pa sa pangatlo, so 1:1 na to. I hope you can. Ganyan lang nag-work yung gears na yan. Ano? Gears are interesting. Tandaan niyo pa ba yung basic concept ng gears? This is a mixer, no? So the larger gear has 40 tooths, no, 40. Tapos the smaller one, the smaller gear, I hope you can see the smaller tooth. The smaller tooth is 8 tooth. This is 40. So 40 divided by 8, that's 5. No? Tapos dalawang pairs ng gear. So this is 5 times 5, 40 divided by 8 times 40 divided by 8. So, tandaan niyo pa ba? Ibig sabihin nun, pag inikot ko to ng isa, yung mixer dun sa dulo will turn 5 times. So, kaya mabilis yung ikot sa kabilang dulo. Tandaan niyo pa ba mechanics, no? Ano lang yan, no? Di ba? Ratio lang nung number of teeth. Ito. Yung sarilo naman, ganito lang naman yung sarilo. So, sana mag-work. So, ganito lang yung sarilo. Sarilo, parang ito yung, this is the second hands. Halimbawa, ito yung minute hands. No? Tapos I got here a motor. So, as you can see, ganun din to, 8 and 40, 8 and 40, 8 tama. So, parang 25 times na mas mabagal to, no? So, you just make a gear system na halimbawa seconds at saka minute, dapat yung total gear ratio, yung product ng gear ratio ay magiging equal sa 60, no? Parang ganun lang yun. So as you can see, ito yung second hands. Ito yung second hands mabilis, ano? Tapos parang ito yung minute hand, babagal. So ganyan lang yung, that's how the watch work, no? Sayang naman kasi. Lumabas na rin lamang yung gears dun sa ano. So it's quite interesting. I'm interested in gears. May mga mechanical engineering ba dito? Okay? So why do we need to study diffusion? So materials of all types are often heat treated. Why do we need to heat treat it? Kasi, nakikita nyo mamaya, mas mabilis yung diffusion pag mas mataas yung temperature. So, pwede namang hindi nyo heat treat, kaya lang yung production, it will take forever, mabagal. Kaya, definitely, kailangan yung mataas yung temperature. No? Tapos ano ba nangyayari pag may heat treatment? So, halimbawa, nagpo-produce kayo ng carbon steel. Yung maliliit na atoms ng carbon, nagdi-diffuse siya papunta doon sa iron. So, na-occupy niya yung mga interstitial spaces. Kaya mas tumitibay yung iron. No? So, sa semicon naman, meron naman kayong silicon. So, ganun din. Yung boron naman yung nagdi-diffuse papunta sa silicon para ma-build up yung mga vacancies. So, para maging semicon siya. Pero definitely high temperature. Makikita niyo mamaya sa mga example. Ano? Mga 1,000 degrees Celsius yung temperature. Okay, so the phenomena that occur during heat treatment almost always involve atomic diffusion. So, mataas ang temperature. Pag mataas ang temperature, makikita nyo yung diffusivity, no? Nag-i-increase. So, pag nag-increase siya, yung mga atoms, maliliit, mga carbon is relatively smaller compared to your iron, will diffuse or get inside your iron crystal. Ganun yung nangyayari. Often, an enhancement of diffusion rate is desired. So, gusto natin mabilis, no? So, pag gusto natin mabilis, the higher the temperature, the better. Kaya lang, may limit din, ano? Kasi pag natunaw na yung solid, halimbawa, naabot yun yung melting point ng iron, hindi na pwede. Hindi na diffusion yung mangyayari kasi matutunaw na yung iron crystal, ano? So, ang limit natin yung melting point ng iron. So, a little below that, which is about 1,000 degrees Celsius, ano? So, bibilis yung diffusion, pero at the same time, solid pa rin yung iron. On occasion, measures are taken to reduce it. So, kung minsan gusto natin medyo mabagal yung diffusion. Heat treating temperatures and times or cooling rates are often predictable using the mathematics of diffusion and appropriate diffusion constants. So, yung mga cheming, alam yan, ano, pinag-aaralan namin sa transport phenomena. So, ano lang naman yan, simple lang naman yan, Fick's law lang yan, di ba? Fick's law of diffusion. So, yung diffusion rate or yung diffusion flux, directly proportional siya sa change sa concentration gradient, tapos inversely proportional siya sa thickness ng material. So, ganun lang yan. Ano? Fick's law. Yun lang yung mathematics ng diffusion. Tapos, another thing, temperature dependent siya. So, pag tumataas ang temperature, nag-i-increase din ang diffusion. Kaya lang logarithmic, no? Makikita niyo mamaya. Parang yung kay Boltzmann, no? Parang Boltzmann distribution yung equation niya. Yun. Sinasabi dito, the steel gear shown has been case hardened. Yung outer surface niya, tinitreat yun, hini-heat treated siya, and then, anong nangyayari doon, pag mataas ang temperature, yung carbon atom, pumapasok doon sa iron crystal, kaya mas tumitigas yung surface niya, nung gear. That is, its hardness and resistance to failure by fatigue have been enhanced by diffusing excess carbon or nitrogen into the outer surface layer. I hope you're getting this, ano? I hope you're imagining this. Yung interstitial space, yun yung mga empty space. Tapos carbon is a very small atom. Tapos you have iron crystal na imagine nyo naman siguro kung BCC man or FCC. Tapos merong mga empty spaces. Doon pumapasok yung carbon. No? So kaya mas nawawala yung empty spaces. So pag walang empty spaces, nagiging mas matibay yung, nag-i-improve yung strength, no? Nung carbon steel. Diffusional processes conducted at elevated temperature are often utilized to introduce impurity atoms into silicon semiconductors. Ito yung sinasabi ko sa inyo kanina, no? Yung boron, that's the other atom that made up your semiconductor. So under high temperature, it will diffuse into a silicon crystal, tapos i-fill up niya yung mga vacant spaces. Ano? So ganun lamang yung semiconductors. Alam niyo na naman, di ba, pag mataas ang temperature, nagkakaroon ng vacancy. Yan yung kinalculate natin nung last chapter, di ba? QB. So yung vacant spaces na yon, pag nag-introduce kayo ng mataas na concentration ng boron gas, nagdi-diffuse yung boron doon sa loob ng silicon. And that's how you manufacture semicon. Ano? So likewise, the heat treatment of steel and the development of their mechanical properties involves diffusion. So that's why we're studying diffusion. So, syempre, theoretically, gusto nating malaman kung gaano ba natin katagal i-heat treat yung steel, gaano ba natin katagal i-heat treat yung silicon vapor, no? Yun yung gusto nating i-solve dito. Okay. So, ito yung illustration, diffusion in solid. This is copper and nickel. So, at low temperature, as you can see right here, ito yung copper, tapos ito yung this is nickel, they are in contact. So ito yung phase in contact nila. At low temperature, as you can see, walang nangyayari. Actually, walang diffusion na nangyayari. Even if time passes by, yung nickel hindi siya pumupunta sa copper, yung copper hindi siya pumupunta sa nickel. Pero siguro pag matagal na, siguro isang taon, magkakaroon din ng diffusion yan. Pero syempre, we're speaking of production, industrial production, walang kwenta to sa sa industry, yung low temperature diffusion. So ang meron lang significance, ito lang, yung high temperature. So pag high temperature, yung diffusion significant. So as you can see, yung copper kasi mas mababa yung concentration niya dito sa portion na to, magdi-diffuse siya papunta dito. Yung nickel naman magdi-diffuse papunta doon. So as time passes by, siguro hours lang yan pag mataas yung temperature, magiging ganito na yung structure ng crystal niya, no? As you can see, magkahalo na yung red at saka blue. And then yung concentration, ito yung concentration. Tumataas na yung concentration ng copper doon sa kabilang side. Yung nickel naman tumataas ito sa kabilang side. No? So you really need high temperature for solid diffusion to occur. No? Pero ito dapat, yung temperature na to, hindi naman siya lalampas sa melting point ng metal. Kasi pag lumampas siya sa melting point ng metal, iba na yun, hindi na siya solid diffusion. Yun yung temperature limit natin. Okay, so what are the diffusion mechanisms? The atoms in solid material are in constant motion. So gumagalaw naman yan kasi may energy yan. So they are rapidly changing positions. Yun yung nagkokos ng Kasi nagbabibrate yan eh. Nagbabibrate yung mga atoms. So yung mga PChem, napag-aralan yan sa, hindi nga pala yung inaabot. Ako kasi nag-elective lang ako ng quantum. Pero hindi sa Gen Chem, pwede sa Gen Chem. Meron kasi yung quantum chemistry, tapos sa quantum chemistry, pinag-aaralan yung vibration. Yung mga atoms nagbabibrate. So, because of that vibration, yun yung that's why they are rapidly changing position. Yun yung nagkocause ng rapid change of position, yung vibration. Vibrational energy yan. So, for an atom to make such a move, two conditions must be met. Alam niyo na naman to, enough energy, at saka dapat merong vacant sa katabing position. No? So there must be an empty adjacent site. Yun yung number one prerequisite para magkaroon ng diffusion. There must be an empty adjacent site. Na-imagine nyo naman yung crystal. If you have a crystal, tapos halimbawa doon sa katabing site, walang laman, so pwedeng mag-move yung atom kasi nagbabibrate siya. So pwede siyang mag-move doon sa katabing adjacent site. And the atom must have sufficient energy to break bonds with neighbor atoms. Okay? So, alam niyo naman yan, the London Dispersion Force, di ba? Meron silang London London bonding, So, yung mga electrons nila gumagalaw. So, kahit pa paano, meron silang attraction with the neighboring atom. Pero mahina lang naman yun. So, pag mataas yung temperature, mataas yung vibrational energy niya, mataas yung vibration niya, pwede siyang kumawala dun sa band na yun and then lumipat sa kabilang position. Ganun lang naman yun. And then, pag mas mataas ang temperature, mas mataas yung energy na available. Kaya, pag mataas ang temperature, may diffusion na nangyayari. So, this energy is vibrational in nature. So, as I've described before, at a specific temperature, some small fraction of the total number of atoms is capable of diffusive motion by virtue of the magnitudes of their vibrational energy. So ang nagkakos actually ng vibration ng diffusion sa solid ay vibrations, no? Vibrational energies. I imagine naman na nagbabibrate yung isang atom, tapos may tendency siyang lumipat doon sa kabila because of that vibration. So mas mataas ang temperature, mas malakas yung vibration niya. So mas malakas yung tendency niya lumipat. Kaya mas mabilis yung diffusion. Kahit na solid lang. Solid pa rin yung physical state. Okay, this fraction increases with rising temperature. So mamaya makikita niyo yan. Meron tayong parang Boltzmann equation for temperature and diffusivity. Nag-i-increase ang diffusivity with increasing temperature. You'll see the Boltzmann equation later. Okay, so what are the two diffusion mechanisms? The first one is vacancy diffusion. So pag vacancy diffusion, as you can see, we have a pure crystalline metal structure. Tapos, as you can see, merong vacant space dun sa kabilang unit cell. So, ang tendency, nagbabibrate tong atom na to, may tendency siyang lumipat dun sa vacant space. So, that causes diffusion. Ang tawag dito is vacancy diffusion. Yun lang kasimple. Tapos, the other one is interstitial diffusion. So, pag interstitial diffusion naman, as you can see, we have a smaller atom right here. So, for example, carbon, tapos this is our iron. So, carbon is smaller than iron, di ba? Ang atomic mass ng carbon, 12 lang. Ang iron, 55. So, maliit lamang tong carbon. So, a movement ng carbon is from one interstitial space to another interstitial space. Yung interstitial space, as you can see from this illustration, yun lang yung mga empty spaces between the atoms. So, halimbawa, imagine niyo FCC, no? So, FCC dun sa gitna, 'di ba, may interstitial space, So, yun, gumagalaw dun yung mga carbon. So, pag BCC naman, dun sa phase naman yung empty. So, dun gumagalaw yung carbon, no? Okay. Hydrogen, carbon, nitrogen, oxygen. Ito yung mga maliliit na atoms, which have atoms that are small enough to fit into the interstitial position are able to do interstitial diffusion. Okay. So in most metal alloys, interstitial diffusion occurs much more rapidly than diffusion. I mean, vacancy diffusion. Mas mabilis to. Kasi palaging available ang interstitial space. Kaya mas mabilis yung interstitial diffusion. Kung makikita niyan mamaya, i-compare natin yung diffusivity ng interstitial diffusion at saka yung diffusivity ng vacancy diffusion. Mas mataas yung interstitial diffusivity. So furthermore, there are more empty interstitial position than vacancies. Okay? So ito kasi permanente ito yung nature ng, kung tatandaan nyo pa yung nature ng metallic crystalline structure, meron talagang mga empty spaces, no? So this is not by chance like vacancy. Ang vacancy kasi, kung natatandaan nyo, konti lang yung vacancy. So, kaya mas mabilis yung interstitial diffusion. Hence, the probability of interstitial atomic movement is greater than for vacancy diffusion. Okay? So, I hope you can imagine this. Kung bakit mas mabilis yung interstitial diffusion. Siyempre, ang significance niyan, mabilis lang gumawa ng carbon steel. Kaya yung carbon steel, relatively mas mura siya. No? Okay, so let's go to the mathematics. Let's define diffusion flux. So, yung mga chemeng, alam niyo yan, pag flux per unit area. Mass flow rate per unit area. So, this is our definition of flux. So, this is the symbol for flux. J, no? We're going to call this diffusion flux. Okay, J. Tapos M is mass. This is in kilogram or in gram or in pounds. Tapos per unit time. So M divided by T, this is mass flow rate. Tapos pag dinivide nyo ng area, kung saan siya nagpo-flow, siya nagka-transfer, that is a flux. So, The units for J or for flux are, for example, kilograms or atom per meter squared per second. Kilogram per meter squared per second or atoms per meter squared per second. Ito yung unit. Ano? So actually, pag atoms per meter squared per second, pwedeng yung M kasi, actually mas standard na definition yun. Ano? Sa Chem, alam namin, yung standard definition is, alimbawa, kilogram, mole, mole, mas standard definition yun. Pero dito, dinefine niya na in terms of mass. Kasi nga, mas practical yung mass. mas nakaka-relate yung ibang engineering courses sa mass. So, sa Chem, kami, mas nakaka-relate kami sa mole. Kaya, ang standard sa amin ay yung mole, kilogram, mole, pound, mole. Pero sa ibang engineering courses, mas nakaka-relate sila sa kilogram, pounds, diba, grams. Kaya ito yung standard definition ni Alistair. Mass per unit area per unit time. Yun yung flux. I hope you can remember this. Ano? Yun lang naman. Okay. Fick's law of diffusion. So, sabi ng Fick's law of diffusion, as you can see from this equation, yung flux daw is directly proportional, no, sa concentration gradient and inversely proportional sa thickness ng material. So, J is equals to negative D, dC dx. C is concentration, ano? X is the thickness. D is diffusivity. So, diffusion flux is directly proportional to concentration gradient and inversely proportional to thickness of the material. So, the constant of proportionality is known as diffusivity, D. No? So, mamaya makikita niyo yung unit nito. Ano ba? Centimeter squared per second. Meter squared per second. Okay? Ano pa ba? Feet squared per second. Usually, SI. SI yung unit ng diffusivity. Sa amin, sa camping. Usually, centimeter squared per second. Anyway, makikita niyo naman mamaya, may table tayo. Concentration. Ang concentration pwedeng molarity. No? Ganon. So, mole per liter. Tapos ito naman, thickness, pwedeng inch, meter, feet, kahit anong unit ng length or thickness. Okay, so ba't na yung negative? Parang ano lang to, directional lang to. Ano? Kasi parang ang diffusion syempre, galing doon sa mataas na concentration papunta doon sa mababa. So, mataas, papunta sa mababa, negative itong dC dx. Ganyan, kaya may negative doon. No? I hope you can remember the Fick's law of diffusion. Ang sinasabi lang naman ng Fick's law of diffusion is the driving force of diffusion is the concentration gradient. So, ano bang ibig sabihin nito? Parang ano lang to, i-analogize nyo lamang sa heat transfer. Paano ba ang heat transfer? Ano ba ang driving force ng heat transfer? Di ba ang driving force ng heat transfer ay difference in temperature? So pag itong isang surface mainit, tapos yung kabilang surface malamig, so magta-transfer yung heat from this surface to the other surface. Ano? So ganun din lamang yung diffusion. Pag mataas ang concentration dito mababa, magta-transfer yung material from this area to this area. Ganun lang yan. The driving force of diffusion is concentration gradient. Tapos yung rate naman niya, depende sa thickness. Siyempre, pag manipis siya, mabilis lang. Pag makapal siya, pabagal. No? Ganun lamang yung Fick's law of diffusion. I hope, logical naman to. Hindi naman siya counterintuitive. So, madali lang yung intindihin. Ang problema lang dito is pag medyo bago sa inyo yung concept. Anyway, so we will try to solve this problem. As you can see, just like our previous problem, direct substitution lang naman sa formula. So pag yung diffusivity naman natin ay constant, no, as like most of the cases, halimbawa, constant naman yung temperature. Sa industry naman, they make a way na constant yung temperature sa operation. So pag ang diffusivity natin constant, tapos yung concentration constant din, that's how, sa cheming, palagi lang namang steady state, mas ano kasi yan, control yung, we wanted quality products. So pag quality products, dapat talaga mas simple pag constant lang yung condition. So, mas simple pati yung mathematics niya. Mas consistent pati yung quality ng product. So, kaya your equation is simplified into this. J is equals to negative D Ito yung concentration gradient, Ca minus Cb. Ito yung thickness niya, Xa minus Xb. No? Ito lang yung gagamitin natin equation. So let's look at the problem. A plate of iron is exposed to a carburizing, carbon-rich atmosphere on one side and a decarburizing, carbon diffusion atmosphere on the other side at 700 degrees Celsius. If a condition of steady state is achieved, calculate the diffusion flux of carbon through the plate if the concentration of carbon at position 5 and 10 millimeter, okay, beneath the carburizing surface are 1.2 and 0.8 kilogram per cubic meter. So ito yung unit ng concentration. Ano kilogram per cubic meter respectively. Assume a diffusion coefficient of 3 times 10 to the negative 11 meters squared per second. Ito yung sinasabi ko sa inyo kaninang unit ng diffusivity. Meter squared per second, centimeter squared per second at this temperature. So just simply substitute all the given to this equation. So D is negative 3 times 10 to the negative 11. Ito yun, meter squared per second. Tapos, C is 1.2 and 0.8 kilogram per cubic meter. Tapos, in terms of meter, this is 5 times 10 to the minus 3 meters. Tapos, this is 10. Yung 10 millimeter is equivalent to 10 to the minus 2 meters, a minus. And then just use your calculator to get the final answer. So, tingnan nyo yung units, no? Magka-cancel out yung meters. Ito yung meter nito. Ito, itong meter squared at saka yung meter cube. So, isang meter na lang yung matitira. Tapos may meter ka pa dito. So, this is meter squared. Ano? I hope you can. Tapos seconds. So that's is kilogram per meter squared per second. Ito yung unit natin ng diffusivity, kilogram meter squared per second. So let me double check that value. Pero pabig nga ang calculator. Sa bag ko meron. Na-imagine nyo naman yung problem, mataas yung temperature, 700 degrees Celsius, tapos yung concentration dun sa isang side ng carbon, mataas. Carbon, usually coal yan, hinahalo lang nila sa iron. So coal is carbon. Sa kabilang side, mababa. Pag ganyan kataas yung temperature, nagiging gas siguro yung carbon. Sa kabilang side, mababa. So, magdi-diffuse yung carbon dun sa iron. Kasi lilipat siya sa kabilang side. Okay, yung iba may iwan mismo dun sa iron crystal. So, na-imagine nyo magdi-deposit siya dun sa mga interstitial space ng iron metal, iron crystal, kaya mas titibay yung iron. That's quite important. Hindi naman masyadong mahalaga yung mga calculation na yan. Ang mahalaga yung ma-realize niya na kaya tumitibay yung carbon steel kasi yung interstitial space na filled up ng carbon. Diba? Yung mahalaga dyan. Pag nag-work na kayo. Yung kailangang matandaan. Let's just confirm the calculation. 2.4 times 10 to the negative 9. Karsa pa nga, glasses. Salamin. Salamin.
Akin to.
Wala na. Times 10 to the negative 9. Yeah, that's correct. Okay, so simple enough. So expect this in your midterm. Okay, so let's go to our next slide. So what are the factors that affect diffusivity? So dalawang factor, syempre yung natin, i-consider natin. First is the diffusing species. So, in other words, sa chemeng, ano to, size, no? Kung gaano kaliit. Siyempre, pag mas maliit, mas mabilis siyang mag-diffuse, no? So, kita nyo, bakit ba mas mataas ang diffusivity ng carbon compare mo sa iron? Kasi maliit siya. Ganun lang naman yan. Pero dito, sinabi niya, diffusing species. Pero it boils down to the size of the atom, no? The diffusing species as well as the host material influence the diffusion coefficient. So for example, there is a significant difference in magnitude between self-diffusion and carbon interdiffusion in iron at 500 degrees Celsius. Okay. Pag sinabing self-diffusion, ibig sabihin yung carbon mismo, magdi-diffuse siya dun sa carbon crystal. O, siyempre, yung carbon crystal, kung may carbon crystal man, maliit yung interstitial space niya. No? Pero pag yung carbon magdi-diffuse sa iron crystal, malaki yung interstitial space. So, mas mabilis, mas mataas yung diffusivity ng carbon. Okay? Yan yung sinasabi niyo dito. The D value being greater for carbon interdiffusion. So, pag sinabing interdiffusion, nagdi-diffuse yung carbon sa ibang material. Bawa iron. No? Mas mataas yun compared dun sa self-diffusion. Bawa carbon magdi-diffuse sa kapwa niya carbon. O iron magdi-diffuse sa kapwa niya iron. No? A contrast between rates of diffusion via vacancy and interstitial mode. Pag yung carbon kasi magdi-diffuse sa iron crystal, interstitial yon. Mabilis yon, di ba? Kasi maliit lang yung carbon tapos palagi pang may interstitial space. Kaya mabilis. Pero halimbawa, yung iron, magdi-diffuse siya dun sa mga vacant spaces. Mabagal lang yon kasi hindi palaging available yung vacant space. Di ba? So, self-diffusion occurs by vacancy mechanism, kaya mabagal. Whereas carbon diffusion is in iron is interstitial. Kaya mabilis. Okay? So that's one factor regarding diffusivity, diffusing species. Okay, siyempre, the second factor is temperature. So, ito yung sinasabi ko sa inyong Boltzmann equation ng diffusivity. So, DO is a temperature independent pre-exponential. Ito yung parang sa 0 degrees Celsius, ano, ganun. Makikita nyo mamaya may table tayo ng DO. Pre-exponential factor, ano? Parang diffusivity at 0 degrees Celsius. Ganyan sa amin, sa Kemen. O kaya, pwedeng, depende kung ano yung reference temperature nyo, ano? Depende sa table. So, yun. Unit niya, meters squared per second. Tapos QD, this is the activation energy for diffusion. Ano? Tapos R is the same gas constant, 8.314 or 8.31 joules per mole per Kelvin or 8.62 times 10 to the minus 5 electron volt per atom per Kelvin. Yun yung dalawang natin, unit ng R. Tandaan nyo pa yung R? Ano lang naman to, R right here is gas constant talaga. Yan. Gas constant din yung 8.62. Di ba parang K yun? She's supposed to be K. Anyway, I'm going to compare kung K yan or R. Kasi kung R, tama yung 8.314. Yung R, yung ginamit niya is 8.314. So it's probably it's R. No, it's R.
Okay.
Kasi yung Q ay joules per mole. Okay? So joules per mole tapos times 10. Huwag na muna natin i-consider yung yung 8.62 times 10 to the minus 5. Yun na lang munang R na muna yan, 8.314. Parang typographical error ata ito. Kasi K yan yung 8.62 times 10 to the minus 5. Okay? So, yun munang gamitin natin yung R, 8.314 joules per mole per Kelvin. Tapos T is absolute temperature Kelvin. Okay? So, syempre, pag tumataas ang temperature, tumataas ang diffusivity. Kasi may negative Tapos, pag nilipat niyo yung negative sa taas, directly exponential siya with temperature. No? So that is why when we do carbon, when we produce carbon steel, mataas ang temperature. When we try to produce semicon, mataas ang temperature. Yan. So, tumataas kasi ang diffusivity pag tumataas ang temperature. Boltzmann equation. Ano? Boltzmann distribution equation. I hope you get this in your mathematics. Ano? Kami sa physical chemistry namin nakukuha si Boltzmann. Ano ba ang reference niyan? Matandang ano na yan kasi matandang observe na nila yan eh. Pero kay Boltzmann lang pinangalan. Walang derivation. Ano yan? Parang observation. Okay, ito yung sinasabi ko sa inyong table. So, nasa libro naman to. Okay, nandito naman sa PowerPoint. Upload ko na naman yung PowerPoint. So, pag merong problem, you are asked to calculate diffusivity, dito nyo kukunin yung pre-exponential factor. Ito yung pre-exponential factor. So, depende, halimbawa, ito yung carbon yung diffusing species, nagdi-diffuse siya sa alpha ion, no? So, magkaiba kasi yung alpha at saka gamma. FCC ata yung isa. Ito, FCC yung gamma, Ito, BCC. So, ayun, Yung alpha ay BCC. Yung gamma ay FCC. So, alin ang mas mabilis? Ang diffusion. Mas mabilis mag-diffuse ang carbon sa this one. Sa gamma. Sa FCC. Mas malaki yung vacant space doon sa gitna. Ito, mas compressed kasi yung BCC. Occupied niya yung gitna. Yung mga ano lang, yung nasa phase lang yung medyo may vacant. Mas mabilis dito. Iba-iba pa. Copper and copper. Mabilis din, Zinc and copper. Pero ito mabilis to. Pero as you can see, yung kanyang activation energy mataas. Diba? Compare mo dito sa carbon. Mababa lang yung activation energy niya. Lalo na dito. So, kaya mababa yung konting increase lang ng temperature, magdi-diffuse agad yung carbon. Kahit na yung diffusive, yung kanyang pre-exponential factor, mababa. You might be comparing the two. Ito yun. Itong sa ano yan. Ito meron. EV per atom. Ito tama na siguro to. Gas constant ito in terms of EV per atom. Hindi. This is the QD. Meron lamang ditong sample values. May sample values lang tayo. Specific temperature, ito yung diffusivity. So just use the Boltzmann equation to calculate the diffusivity. The actual diffusivity at the specific temperature. Ganun lang naman itong carbon natin. So, mag-refer na lang kayo dito pag merong problem na hinahanap yung diffusivity. Tapos hindi given yung pre-exponential factor pati yung activation energy. Okay, so kamukha nitong problem na to. So gagamitin lang natin yung Boltzmann equation. Using the data in table 5.2, compute the diffusion coefficient for magnesium in aluminum at 550 degrees Celsius. So here's going to use the previous equation. This one, D is equal to DO, E raised to negative QD divided by R2. So, ano yung kailangan natin? Kailangan natin ay magnesium in aluminum. Magdi-diffuse yung magnesium sa aluminum at 550 degrees Celsius. So, ito yung equation natin. So, ang hanapin natin yung DO sa table. So, magnesium in aluminum. So, ang DO niya ay 1.2 times 10 to the negative 4 meters squared per second. Okay? 1.2 times 10 to the minus 4 meters squared per second. Tapos, ito QD. Ang QD ay, ito 131 kilojoules per mole. So, kung joules per mole, 131,000. 131,000 joules per mole. 8.31 na lang ang gamitin nating gas constant, may negative ton. So, mga KMN, medyo bawasan natin. Gamitin, kasi para kamukha tayo ni Callister. 8.31. Kasi kami 8.314. Actually, mas logical nga ito. Kasi kung natatandaan yung mga KMN, nung nag-advance yung calorimetry, na-determine nila na at different temperature, iba-iba yung gas constant. So, kaya ito, nilimit na lang nila sa 8.31 para kahit pa paano, accurate pa rin siya. No, yun yung logic nitong 8.31. Tapos yung temperature na 550, convert nyo sa Kelvin, 550 plus 273. So you'll have this. This is the diffusivity. Confirm natin sa calculator. So 1.2 exponent minus 4. Tama naman ng unit, ano? Ang kailangan lang dito, ito ka, the same unit, meters squared per second, the same unit as the pre-exponential factor. Kailangan lang dito mag-cancel out. It's obvious na magka-cancel out yung joules, saka yung moles, at saka yung Kelvin. So wala nung unit to. So ito na lang talaga yung matitira. So 1.2 times 10 to the minus 4 times shift E, tapos negative 131,000, tapos divided by 8.31, tapos times parenthesis 550 plus 273 parenthesis. Okay, so I'm getting 5.76 times 10 to the minus 13. It's approximate. Pag niround up nyo, 5.8 times 10 to the minus 13. Okay? Dali lang naman, ano? Kaya niya sa midterm. Okay, so on the next video, probably I'm going to discuss chapter 6, no? Tapos, bali itong video na to, expect this on the midterm.
Hey, stop doing that!